is about graphing linear inequalities in two variables. The solution to a linear inequality in two variables is an xy pair that gives a true statement when plugged in. So any xy pair that you plug into this example here that results in a number greater than 8 would be a solution. So there might be an infinite number of solutions. All we're asked to do here is check the two that were given and see if either one of these is a solution. So remember that every ordered pair is x comma y. So when you plug these in, the 6 is our x, the -3 is our y. We'll plug them into the inequality. Use parentheses when you substitute to show work. Simplify the left side of this inequality. 18 plus -12. 18 plus -12 is 6. Is 6 greater than 8? You're checking on the truth of that statement, and it is a false statement. Therefore, this is not a solution. Let's check the second one here. Plugging in -3 for x, 5 for y, to see if it comes out greater than 8. This is -9 plus 20. -9 plus 20 is 11, and is 11 greater than 8? Yes, it is. So this is a solution. It's just one of many solutions, right? This one does work. The graph of an inequality, when you put it on the coordinate plane, is a visual way of showing the set of every single point on the coordinate plane that works in the inequality. So that is a solution. So to graph an inequality, you want to start by graphing the boundary line. To graph a boundary line, you graph it the same way you would graph any line. I like to graph my lines by getting y by itself and using slope and intercept, so that's what I'm going to do. I want to start by getting y by itself, putting this in mx plus b form. So -2y less than -5x plus 8. Looks like I'm going to be dividing by a negative, so I have to remember to switch my inequality sign when I do that. So y is greater than, right? I'm going to switch colors to show you here. I have switched the inequality sign because I divided by a negative number. Simplify the right side, 5 over 2x minus 4. There's my boundary line. I'm going to put that on the graph using the intercept, which is at -4, and the slope, which tells me to go up 5 over 2. Up 5 over 2 again. Be very careful here and pay attention to the sign that you have. Because y is greater than that boundary line, but it's not including that boundary line, right? It does not say greater than or equal to. It just says greater than. When I connect those dots, I need to connect them using what's called a dotted line or a dashed line. It looks kind of like the lines you would see on a highway, to show that that's the boundary of my solution set, but the solution set doesn't actually include the points on that line. But it is going to include all of the points to one side of that line. It's called a half plane. To figure out which side I'm supposed to shade in, I'm going to test a point, plug it into the inequality, and see if it works. And if it works, and it's part of the solution set, then I want to shade towards that point. It is always easiest to plug in 0, 0, as long as that's not on the boundary line. And as you can see here, 0, 0 is not on the boundary line, so I'm going to plug it in to the inequality. I'll plug it back into the original one. Though you could plug it into your modified one if you're 100% sure that it's correct, but I'll plug it into the original one. So if I plug in 0, 0, and you can do this step mentally, but I will write it down to show you what I'm doing. Plugging in 0, 0 is really simple because typically one-sided equation just becomes 0 here. So we have 0 minus 8. 0 is less than 8. Check if it's true. Sure enough, 0 is less than 8, and that means that 0, 0 is part of the solution set. So if 0, 0 is part of the solution set, then the direction that I want to shade is towards 0, 0. Everything on this side of the dotted line is a solution to the inequality. So I am shading in the half plane that represents the solution set. So when you shade, try to do it neatly to show that every point that's kind of to the left of this boundary line here is a solution to this inequality. This is an example of a horizontal and vertical line inequality. We'll start by graphing y is less than -2 on this coordinate plane on the left. Remember that y constant equations are horizontal lines, just kind of counterintuitive. It's the set of all points that have a y value of -2. Now, because it's a less than sign and not a less than or equal to sign, I'm going to draw a dotted horizontal line or a dashed horizontal line to show that I'm not including the points on the line. And I need to shade the solution set of everything that is less than that. So I don't even need to test a point here because I can see less than that. For y values less than that, I want to shade this direction. And and that is the half plane that represents the solution set. And the other coordinate plane, I'll do the next line, which is x is greater than or equal to -5. X constant equations are vertical lines, so this is the vertical line. Every number that has -5 as its x value, or every point that has -5 as its x value. And this time my boundary line can be solid because it does include the -5, as you can see, because that sign has an equal sign underneath it. I should be using a ruler to make that a bit neater, but that's the boundary line, and I'm supposed to shade everything greater than it. And so we're looking for x values that are greater than -5. We're going to be talking about everything on this side of our boundary line. And that is the solution set to that inequality. And this is just a bit of an extension here. It's an absolute value graph. So we've learned how to graph absolute value equations in a previous video. To graph an absolute value equation, you have to remember that it's shaped like a V, and you want to find the vertex first. And this time, the vertex is going to be located at -1, 5, because that is h and k, our horizontal transformation and our vertical transformation. I'm going to find that point, -1, 5, put it on the graph. The -2 that's in front of the absolute value bracket is kind of like my slope. It tells me to go down 2 and over 1 in both directions in order to get the V shape. And this is my boundary V. So I want to check and see whether my boundary is dotted or solid here. Because the greater than sign does not have an equals underneath it, this is a dotted V, or a dashed V, and it does not, the solution does not include the points on the V. It either includes the points inside the V or outside the V, is how I like to think of it. So this is a little bit different from just a line when you shade one side of it or the other. This time I want to choose a point that's inside our V, and if that point works, then I'm going to shade all of the other points inside of V. And if it doesn't work, I'll shade outside the V. So I have 0, 0 here inside the V. I'm going to choose that, plug it into the original equation, and see if it works. I do want to show my work for this. These equations inequalities are a little bit more complicated because of the absolute value bracket. So do show your work. When you plug in 0, 0 here, follow the order of operations. Do what's inside the absolute value brackets first, as if they are parentheses. 0 plus 1 is 1. The absolute value of 1 is just 1. And -2 times 1 is -2. So fully simplified, this inequality now reads 0 is greater than 3. Well, 0 is not greater than 3. That is a false statement. And therefore, the point 0, 0 is not one of the solutions to this inequality. And that means I need to not shade the points inside. I need to shade all the points that are outside of this V. And this one can look a little bit funny, because the solution includes every point that's out here, and not the points that are underneath or inside of the V. Okay? I erase my little circle around 0, 0 since that did not work, and that's a graph of this solution set. That is all.